Okay, we have a lot of examples to do today as we learn the definite integral and the fundamental theorem of calculus. It's absolutely necessary that you go through the note cards before watching this video to make sure that you have an understanding of each of the rules we're going to be working with today. So, to start out, we're going to do our first example, which is to calculate the integral from 1 to 3 of 4 dx. Now, the numbers on the upper and lower limits of integration tell us where we start and end taking the area underneath the function, or more accurately, the area between the function and the x-axis, and it is assigned area, so above the x-axis will be positive and below will be negative. So this function would be y equals 4, which is just a horizontal line, very boring function, which you could see right here on the graph. Now, I'm going to find the area from 1 to 3. These are x values, so from x equals 1 to x equals 3, so it's as if I draw vertical lines, and I'm finding the area bounded by our function, these x values 1 and 3, and the x-axis. So we just use an area formula from geometry to calculate this. This would be a rectangle with a width of 2 and a height of 4, and 2 times 4 would equal 8. So that answer for that integral problem is 8. Alright, let's try another one. Example 2. The integral from 0 to 3 of x plus 2. So, graphically, I'm going to sketch the function. So, starting with a y-intercept of 2, of course this is y equals x plus 2. Oh, and I forgot my dx. Y equals x plus 2 has a y-intercept of 2 and a slope of 1. So that's going to go like this. And I'm finding the area from 0 to 3. Oops. Which would look like this. So this area would be a trapezoid, and we know that the formula for area of a trapezoid is 1/2 base 1 plus base 2 times the height. So this should be 1/2 times first base be 2, second base be 1, 2, 3, 4, 5, and the height would be 1, 2, 3. So the area would equal 7 times 3, which is 21 over 2, which is 10.5, and I don't care whether it's a fraction or decimal. So this would equal 10.5. Alright. 3. How about the integral from -2 to 2 of the square root of 4 minus x squared dx? Now, graphing this function may not be as quick for you right off, but I think that you'll see if we had y equals the square root of 4 minus x squared, this would look a little bit more familiar to you if you first squared both sides. So you had y squared equals, equals 4 minus x squared, and then added x squared to both sides, so x squared plus y squared equals 4. Now this should look very familiar. That is the equation of a circle. That was not a very straight line I just drew. And the circle is centered at the origin and it has a radius of 2, because if you'll remember the formula was x squared plus y squared equals r squared. So the radius is 2. Now the only thing about this is when we started up here, this was only the positive root. So we're actually not talking about the whole circle. We're talking about a half circle, the upper half of that circle. So this is a semicircle. If it had been like the positive or negative square root, it would have included the bottom. But this is just the positive portion. So we're finding this area. And how do I find the area of a semicircle? Pi r squared divided by 2. So this would be pi times 2 squared divided by 2, which is 4 pi divided by 2, which is 2 pi. So this equals 2 pi. Alright. Example 4 is the integral from -3 to 3 of 2/3 x dx. So if I make a graph of this, this is a line with a y-intercept of 0 and a slope of 2/3. So that's going to look like this. And I'm calculating the area from -3 to +3. Now, this is the area between the x-axis and the curve, so down here and up here. Now, these are triangles, so base times height divided by 2 is how we'd calculate the area. So this one would be 3 times 2 divided by 2, so that would have an area of 3. So this one's area is 3. However, this one's area down here, even though it also has a base of 3 and a height of 2, this one's area is -3, and the reason is it's below the x-axis. So that's what we mean when we say signed area. So if I take my -3 and add it to my +3, the net signed area is equal to 0. So very important that you pay attention to whether the area between the curve and the x-axis occurs above the x-axis or below the x-axis. Alright, those are all the examples we're going to do with finding areas. Now we're going to use some of our properties of the definite integral. So on example 5, what if I take the integral from pi to pi of the tangent of d theta? Well, notice that my starting point and my ending point are the same. That gives me no room to open up an area at all. So this one is equal to 0. And anytime my upper and lower limits of integration are equal to each other, that's always going to be 0. Now, number 6 has the integral from 3 to 0 of x plus 2 dx. This ought to look familiar to you because it's very much like example 2 that we did, 0 to 3 of the function x plus 2. The only difference here is that the order is reversed. Here I've got the 3 on the bottom and the 0 on top. Does that matter? Yes, it does. We always want to have our larger number on top and our smaller number on bottom. So we can rewrite this one with the limits of integration switched by changing the sign in front of the integral. That comes from one of our note cards for today. So this would be the opposite of the answer that we got for example 2, which was 10.5, and that was found by calculating the area on a graph. Okay, example 7. if we let's see, the integral from -2 to 3 of f of x dx equals 7, and the integral from 1 to 3 of f of x dx equal 4, they ask us to find the integral from 3 to 1 of f of x dx. So, for this one, notice it's the same thing here as it is up here, except for we've switched the upper and lower limits of integration. So that means all I have to do is change the sign on that answer because of the property that we talked about in our last example. Now, example 8 is going to use the same starting information that we have here at the top. And it says evaluate the integral from -2 to 1 of f of x dx. Now, we don't have a -2 to 1, but I do see a -2 down here and a 1 down here. So we can use this to help us write a sum of two integrals that will calculate this one using the additive interval property. So the way the additive interval property works is I want my lower limit right here to be the lower limit on my first integral, so I'm going to use that -2 to 3 since they gave that to me. And then I want this number up here to match this number down here and finish off with my upper number right here. So if I switch this one to 3 to 1 like I had on example 7, which means I need to change the sign on the starting premise one, which we've already figured out comes out to -4. We can add these two integrals to get the result of the -2 to 1. And so the -2 to 3 integral equals 7 plus the 3 to 1 integral is -4. So the overall result here is 3. Alright. Number 8. No, that was number 8, sorry. Number 9. Says if we have, and this is the same starting information, the integral from -2 to 3 of f of x dx equal to 7, and the integral from 1 to 3 of f of x dx equals 4. Evaluate the integral from 1 to -2 of f of x dx. Now, this one could be done by setting up the additive integral property just like we did in the last problem, but this one is exactly the flip-flopped order of the limits of integration from the last problem, so the answer should just be the same but the opposite sign. If you wanted to go about setting it up as a sum, you would want your 1 on the bottom, so you'd start with the 1 to 3 of f of x dx, plus you'd want the 3 on the bottom here, the 3 to the -2 on top here of f of x dx, and that means that you would take 4 plus the opposite of 7 to get -3. But that, of course, that's not necessary after having finished example 8. Okay, number 10. Let's say that the integral from 2 to 5 of f of x dx equals 5, and the integral from 2 to 5 of g of x dx equals -3. Evaluate the integral from 2 to 5 of 4 times f of x. Well, whenever you have a constant in front of that function, that constant can come out in front of the integral symbol, so your scalar multiple can become a multiple of the integral itself. We already know that the integral from 2 to 5 of f of x dx is equal to 5, so we just replace that integral with 5. 4 times 5 equals 20. Okay, now number 11 is going to use the same starting information. So I'm going to keep working right here. Number 11. The integral from 2 to 5 of f of x plus g of x dx. Now, this means that you can just add these two integrals as if it said the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of g of x dx. And you don't necessarily have to write out that step, but that's essentially what we're doing here. So this would be 5 plus -3, which equals 2. Okay, and now we're going to start with that same information for example 12. Okay, so number 12 says to find the integral from 2 to 5 of f of x plus 3 dx. So this could be the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of 3 dx. So this would equal 5, and this would be a rectangle if you think about it graphically. Y equaling 3 going from 2 to 5. Actually, it's a square. The base is 3. The height would be 3. So the area would be 9. So 5 plus 9 is 14. Example 13. Wait. I'm going to erase this because it uses the same starting information. 13 is the integral from 2 to 5 of f of x plus x dx. So, again, this can be split into two separate integral problems. And the first one would equal 5. The second one you'd do graphically. That's a 2 to 5 trapezoid. So it would be 1/2 base 1, which is 2, plus base 2, which is 5, times the height, which is 3. So that's 5 plus 10.5, which equals 15.5. Alright, now number 14, the last one with this startup information. And the last one we're going to do using properties. Is the integral from 5 to 2 of f of x dx. Now this is a lot like the first one that they are giving you here. So the only difference is that the limits are switched, the upper and lower limits. We have our larger number on bottom. So we're going to switch the limits by putting a negative in front. And then that'll be -5. Alright, so that is how we calculate definite integrals. If you think about the difference between an indefinite integral and the definite integral, there are quite a few differences. For one, you've got boundaries on your definite integral. We didn't have those when we were doing indefinite integrals. The answer is an area, whereas the answer to an indefinite integral was an antiderivative. The answer is numerical when we're doing a definite integral, and the answer was some type of function when we were finding an indefinite integral. Sorry, the answer to a definite integral is a number. And there's only one solution to one of these problems, where there are infinitely many solutions to indefinite integrals because you have the plus c on there. So you may ask yourself, why is this even called an integral? How are these two related? Well, that kind of brings us to the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus ties together the indefinite and definite integrals, and it looks like this. The integral from a to b of f of x dx, which could represent any definite integral, is equal to capital F of b minus capital F of a. And if you remember, that capital F means the antiderivative. So basically what that means is I'm going to find the antiderivative of this function, f of x, plug in b and plug in a, substitute those values into the antiderivative, and subtract them. So let's take a look with example 16 at how that's going to look. I'm going to do the integral from 1 to 4 of 2 square root of x plus 1 dx. Oops, it looks like I skipped number 15, but I'll come back to that. So this would be the integral from 1 to 4 of 2x to the 1/2 plus 1 dx. So if I calculate the integral of that, that's going to be add 1 to my power, 3/2, multiply by the reciprocal of that power, so that's going to be 2/3. 2/3 times the 2 already in front would give me 4/3, plus the integral of 1 is x. Now we don't put a plus c on here when we're using the Fundamental Theorem of Calculus, and we're plugging in the 1 and the 4 to evaluate this. So we're going to say 4/3 of, this could be written as the square root of 4 cubed plus 4 minus 4/3 of the square root of 1 cubed plus 1. So this is 2 to the 3rd power is 8. 8 times 4 is 32 thirds, 32 thirds, plus 4 would be 12 thirds, would equal 44 thirds for this first piece of our work here. And on the bottom, this would be minus 4/3 plus 1, which is 3/3, so minus 7/3. So 44 thirds minus 7/3 would be 37 thirds. I'm running out of room. So 37 thirds is the answer to that. Now let's go and try number 15, the one that I skipped. The integral from -1 to 3 of x squared minus 1 dx. First I calculate the antiderivative, 1/3 x cubed minus x, and I'm going to evaluate this from -1 to 3. That means I plug my 3 in first and subtract what I get when I plug my -1 in. So that's 27 divided by 3 is 9. 9 minus 3 is 6, minus -1/3 plus 1 is 2/3. 6 minus 2/3 would be 5 1/3. So that's the answer there. So in effect, we're finding these areas between the curve and the x-axis without having to draw the curve and use geometry formulas, because honestly we don't really have geometry formulas that are very helpful without using calculus to find these area of these curvy regions. Alright, 17. How about the integral from 0 to pi over 4 of the secant squared of x dx? Well, the integral of the secant squared of x is the tangent of x, and we're going to evaluate this from 0 to pi over 4. So that means I'm going to take the tangent, plug in my upper limit, pi over 4, minus the tangent with my lower limit plugged in, 0, which is going to be 1 minus 0, which equals 1. Alright, our last example is one in which we're dealing with the units of the definite integral. When you are finding the area between a curve and the x-axis, you can kind of think of it as finding the areas of these rectangles summed up like we did with our Riemann sums. And so the units for that area is the units of the independent variable along the x-axis multiplied by the units of the dependent variable, which is your y quantity, being multiplied by each other. So let's take a look at an example right quick. This is going to be our last example. And I'm sorry if it's a little blurry, but hopefully you can read it with me. W of t is the rate at which a baby gains weight after birth, where W is measured in pounds per month and t is measured in months since the baby is born. Interpret the integral from 0 to 1 of W of t dt equaling negative 0.127, and interpret the integral from 0 to 12 of W of t dt equaling 9.7. So the question first of all is, we're not calculating an integral. They gave us the answer. They're just saying in terms of the problem, what does this mean? And so what are the units for these answers that they have here? Well, the independent variable is the t, which is in months. So we're going to say months times the dependent variable is W of t, and it's measured in pounds per month. So pounds per month. So if we multiply these, months cancel and it equals pounds. So that means the answers for both of these are in pounds. So what does it mean if the integral from 0 to 1 of W of t dt is negative 0.127 pounds? That means from 0 to 1 in months, so during the first month, this baby loses 0.127 pounds, which is common for a baby to lose a little bit of weight during the first month. They have to work a lot harder. And then in B it says interpret the integral from 0 to 12, so from 0 to 12 months, that's over the first year. It equals 9.7 pounds. That would mean that the baby has a gain of 9.7 pounds over the first year. So that's how you could interpret those. Alright, so I wish you all the best of luck on your work with the definite integral and with the fundamental theorem of calculus. Remember, even though you have learned how to find the integral, the definite integral, using the fundamental theorem of calculus to practice doing some with areas on a graph with the definite integral to start out with, so that you can kind of make those connections that they are going to equal the same thing. Alright, good luck. Bye-bye.